Today on the deep dive, we are setting fire to a core assumption about physics.
A pretty fundamental one.
Yeah, the idea that something that's freezing cold can't possibly ignite anything.
Right.
The sources you shared with us describe this. I mean, it's a completely mind-bending scenario. You take a solid piece of iron,
Sturdy, everyday iron.
you plunge it into a liquid that is nearly 200 degrees below 0 Celsius, and you watch it burst into flames.
Violent, self-sustaining flames. It's an incredible sight.
It breaks your brain a little. Iron is our symbol for strength, for stability. It resists fire. You need a forge. You need immense heat just to get it to glow, let alone actually burn.
Exactly.
So how can liquid oxygen, or LOX, which is at a staggering minus 183 degrees Celsius, how does that act as the hyperaccelerant?
That's the paradox, isn't it?
That's the paradox we're diving into. Our mission is to analyze the chemistry behind this powerful and incredibly dangerous reaction.
And explain how extreme oxygen concentration just flips the whole script.
It turns common iron into a volatile fuel.
It's one of the most counterintuitive things you can study. The cold is the perfect distraction.
A distraction.
Yeah, you see this clear, bubbling liquid. You feel the cold coming off it, and you assume it's inert, safe.
But it's not.
Chemically,
Yeah.
it's anything but.
Okay, let's start right there then. If the temperature is such an extreme red herring, then the basic physics of combustion must be just completely different here.
They are.
So what's the single most important factor that causes this?
It's concentration, pure and simple.
Concentration.
The liquid state is misleading. What you're really looking at is a bath of nearly 100% pure oxygen.
Ah.
And that one fact overwrites all of our normal intuition about temperature.
So let's compare that. The air we're breathing right now, a
Right.
fire in a campfire is burning using what, 21% oxygen?
About 21%, yeah. The rest is
Yeah.
mostly nitrogen, some other inert gases that basically just dilute the reaction. They get in the way.
So if you're submerged in LOX, you're getting rid of that, what, 79% buffer?
And replacing it all with active fuel.
Exactly.
You have almost 5 times the oxidizer packed into the same
Wait,
space.
5 times. Wow.
And it's not just pure, it's also incredibly dense because it's a liquid. You've maximized the availability of the reactant in a way air just can't compete with.
So in that hyper-concentrated environment, the rules just change.
The rules are completely rewritten.
Yeah.
How quickly oxidation can happen, what's required to start it, everything changes.
This sounds like it affects the energy needed to even start the fire. There's a term for that, isn't there? Activation energy.
It absolutely does. And that's a key piece of jargon we should probably unpack for you.
Yeah.
Activation energy is, well, it's essentially the energy hurdle. The minimum spark or heat you need for a reaction to kick off.
The push to get the boulder rolling downhill.
That's a great way to think about it. With only 21% oxygen, iron needs a huge push, a ton of heat, to start combining with the few oxygen molecules around. But when you dunk it in 100% oxygen, you have such an overwhelming supply of molecules ready to react that the hurdle is, well, it's dramatically lowered.
It's just easier for the reaction to start?
Exponentially easier.
What?
To initiate and, crucially, to sustain itself.
So that heavy, durable iron, the sources say its flammability in LOX is like paper.
They do.
But they also stress it's actually far more dangerous. Why is that? Why is a burning piece of iron in LOX worse than, say, burning wood?
It comes down to 2 things, the intensity of the heat and the state of the fuel.
Okay.
When iron burns, it generates incredibly high temperatures, much hotter than organic materials like wood. And because it's a metal, it doesn't turn to ash.
Right.
It burns into particles of molten iron oxide, slag.
Molten.
And when that reaction is supercharged by 100% oxygen, it becomes so rapid, so violent, that it sprays these superheated molten particles everywhere.
So they're not just flicks of ash.
No, not at all. They're tiny, white-hot liquid projectiles. And they can ignite anything else they touch. That's what makes it so uncontrollably destructive.
That makes the danger feel very real. It's not just a fast fire, it's a self-spreading molten fire.
Yeah, the volatility of the debris is what sends the danger level through the roof.
Okay, so this brings us to the next critical point, the visual of it. How does the reaction actually start? We have this frigid liquid. How does it ignite the metal?
That's the magic of the phase change. You need 2 things, the 100% oxygen and a small thermal trigger.
And a trigger could be anything.
It could be as simple as friction, a bit of residual warmth from being held, or even a sharp impact.
Okay.
And here's what happens. When that slightly warm piece of iron touches the LOX, the frigid liquid hits that localized heat, right on the metal's surface.
And oxygen has a really low boiling point.
Very low, -183°C. So that tiny bit of warmth is more than enough to make the liquid oxygen vaporize, turn into gas almost instantly.
So it's not even a liquid where it's touching the metal. It flash boils.
Precisely. It's an incredibly fast, violent transition. You're not getting slow bubbles. You're creating a high-density, high-purity pocket of oxygen gas right at the reaction surface.
And that gas is then immediately consumed by the hot iron.
Yes, turning it into iron oxide.
It's like the iron is creating its own tiny, perfect combustion chamber around itself.
That's a perfect description. It vaporizes the liquid, makes a pure oxygen atmosphere, and then uses that atmosphere to fuel itself. It's a self-feeding loop.
And the supply is basically infinite as long as it's in the bath.
Exactly. The heat from the burning iron just vaporizes the next layer of liquid, which feeds more oxygen gas back to the iron, and the process just accelerates.
That feedback loop.
The ultimate feedback loop.
That visualization really helps. It explains why the speed is so critical. It's not just a burn, it's this instantaneous transformation. And the sources use a specific term for this, which really drives home the force of it. They call it an oxidation blast.
Yeah, that term is chosen very carefully. It's meant to convey the explosive nature of it. The oxidation is happening at what you could call a frantic speed.
It's the difference between steel rusting over years
And iron being consumed in milliseconds.
Yeah.
The energy release is so rapid it can generate shock waves. That's why it's a blast, not just a burn.
So let's zoom in on the spectacle of it for you listening. What does this oxidation blast actually look like?
The descriptions are pretty dramatic. You get a blinding amount of sparks and fire almost instantly.
And you mentioned molten particles.
Yes, and because these particles are tiny bits of superheated molten iron oxide, they look exactly like small fireworks or firecrackers erupting underwater.
So the iron is just tearing itself apart in a shower of tiny red and orange projectile.
That's exactly it. And the colors are fascinating. They're actually diagnostic.
What do you mean?
Well, because the reaction is so hot and pure, the colors of the sparks, the vibrant reds and oranges, can tell you what trace elements or alloys are in the iron.
Because different elements burn at different temperatures and give off different colors.
Exactly. You're watching a kind of high-speed, contained chemical analysis,
Yeah.
all driven by pure oxygen.
That's a great detail. Okay, let's address the elephant in the room here. The hypothetical that sort of defines the boundaries of this danger.
The screwdriver question.
The screwdriver question. What happens if you just drop a regular room temperature screwdriver into a bath of LOX? Does it just explode?
It's an essential question because it defines the threshold. And the sources say no. It won't immediately explode or burn.
Okay.
It'll just get super cooled. We might get a layer of frost on it from the moisture in the air.
There's always a but.
There is. The moment that tool is disturbed, if you move it quickly, create friction, or if it had any residual heat on it, the dynamic changes completely.
So the trigger is key.
The trigger is everything. Moving it, striking it against the side. That can be enough friction heat to start the phase change. The iron is then sitting in 100% oxygen, and the burning begins.
So it's not just iron in LOX, it's the combination of the iron, the pure oxygen, and that thermal trigger.
Precisely. And this is why safety procedures around LOX are so incredibly stringent.
You can't just use standard steel tools.
Absolutely not. In any environment handling concentrated oxygen, especially liquid oxygen, you have to use specialized tools. They're often made of copper, brass, or specific alloys like Monel.
And why those materials?
They're just far less reactive. They require a much higher activation energy to combine with oxygen, even at these concentrations. They're chosen specifically because they refuse to participate in that oxidation blast.
So the big takeaway here is that you can't trust superficial properties. The coldness of the LOX is completely irrelevant.
It is. It's irrelevant in the face of its overwhelming chemical potential. That's why one of the sources calls it a silent fuel.
Silent fuel, I like that.
It doesn't look like fuel, doesn't smell like it, but it holds this potent chemical energy just waiting for the smallest invitation.
It's such a phenomenal reminder that science is full of these surprises that they challenge our daily assumptions. We think frozen things are inert. Cold means safe. But here, the cold is just the mechanism to achieve the deadly concentration.
And that principle goes way beyond cryogenics. You have to train yourself to look past the obvious cues like temperature or what state something is in and focus on the underlying chemistry.
Especially concentration.
Especially concentration and chemical structure. That's where the real potential for risk or reaction lies.
Because if concentration is the master variable, then a slow, harmless reaction could become explosive just by, increasing the density of one ingredient.
Exactly.
This has been a deep dive that fundamentally changed how I think about iron and fire. We started with the paradox. Iron, famously hard to burn,
Igniting instantly.
in a substance that's freezing cold. And the synthesis is actually pretty clear now.
Mhm.
The iron burns not because it's hot, but because it's submerged in nearly 100% oxygen at minus 183 Celsius.
And that combination allows a tiny thermal trigger to cause that instantaneous gasification.
Resulting in a violent, destructive oxidation blast.
That's it in a nutshell.
So let's leave you with this final thought to mull over. If concentration, not temperature, is the ultimate controller of combustion speed, what other factors in common environments, things like high pressure or the presence of simple unseen catalysts, what else might be hiding that same kind of explosive potential?
Makes you wonder.
Yeah, keep an eye out for those hidden sources of silent fuel in places you assume are completely stable.
A great thought to end on.
Thank you for sharing these incredible sources and letting us unpack the terrifying beauty of cold, concentrated chemistry. We'll catch you next time.